Okay, so once again, this is Class D, as in Delta, which means, in short, that we will go through the whole chain from one to the other, to the other, to the other, and at no point until the very end will we try to make RF, or radio frequency. Let me try to demonstrate that here. So here we have a box, and this is, in my case, the SI 5351. I can't write that. I drew the box too small. All you need to know about that is it takes data from, in my case, an Arduino, and power. The Arduino is programming and things like that. It's not really within the scope of this video. What it is a clock generator. Very simply, in the case of 630 meters, or 472 kilohertz, this thing is going to be turning the power on and off at a rate of 472,000 times per second. So just imagine a switch going on and off at that rate. So that's all that is, in short. But it's a very, very weak signal. So then we need to go to a gate driver. In this case, it's the IXXD, and then some numbers. Either way, it's a gate driver. What you need to know about that is that it takes the clock signal out of the SI 5351, adds power, in this case 12 volts, and then swings over a wide range of frequencies, once again switching on and off power, this time more power, at the same rate of 472,000 times per second. And then we go into a MOSFET. In this case, the IRFP 520N, which is not an RF device. It's actually just a power switcher. And then guess what's going to happen to that? Once again, we're going to go in here with some tomfoolery, and we're going to switch it on and off at a rate of 472,000 times per second, plus harmonics and all kinds of stuff like that. So then we're going to put it through a filter, say LCL, 3 inductors, 2 capacitors, inductors in series, capacitors to ground, and that's going to shape our square wave into something that looks like RF. So let's go back over here, excuse me, and try to demonstrate what it would look like on an oscilloscope. If you tapped at this point right off of the SI 5351, you would have something to the effect of, well, we'll make that the 0 line. You would have voltage that ramps straight up, overshoots a little, maybe gets a little fuzzy, goes to a constant amplitude, and does the same thing when it turns off, like a square wave with fuzz all over it. Well, to solve that, we're going to add a little resistor that protects the SI5351 and slows down the fast edges. So after that resistor, we end up with something that looks more like that. Still a square wave, but just kind of with rounded, tamed edges. Then we're going to go over here to the gate driver. Well, it is a fast switching device. So guess what it's going to look like? It's going to be back to very fast edges, very tight square wave, noise, harmonics, all kinds of junk. And then once again, we're going to run it through another resistor, which will then timer down to that, roughly. And then we're going to run it over to the MOSFET. And once again, it's going to be all ugly. We're going to run it to a resistor. We're going to clean it up. And we're left with something like that. Just this ugly, but pretty square wave. Then we run it through our low pass filter, and we get our ugly, beautiful square wave, and we remove the harmonics. Round there and back down. It will probably cross at the same point. My illustration is poor. But if you notice that if you put a few of these together, you have at least a semi-sinusoidal wave. So that's the basic topology of this whole thing. Turn power off at a fixed rate using the clock. Use a gate driver to make that switching more decisive, and then put it into a big power transistor. This is very, very efficient because at no point are we trying to make RF. We're not filtering anything in between. Our resistors that just happen to make the square wave less fast on the edges are really there just to protect each device and just keep it actually functioning. But we make RF at the end, and that's why Class D can be so efficient. In the case of 472 kilohertz, even with a single IRFP 520, there's potential to get somewhere between 100 and 150 watts at 28 volts, which is what I'm going to be doing. But I just thought I would share that because there's a lot of mystique that goes around RF circuits, and it really helped me to figure out what was going on whenever, well, I built this, and then everything started to click, so to speak. In the next video, we'll show what this actually does in reality, because this is all theory. And we'll touch it right now on, you might notice a few extra parts. All we've got are extra capacitors, electrolytics, and just normal ceramics. And all those are doing in this function is decoupling. Decoupling on the power side. Just makes everything quieter. And probably a few other things. I'm not an actual RF engineer. That's kind of the point. So I'm trying to show that you don't need to be to build your own things. Once again, this will have to be very different if you are trying to build this same kind of circuit topology at a different frequency. I can get away with all these flying leads and spaghetti because I'm at such a low frequency. These long wires, quote unquote, look like nothing this low. And even I could still run into problems. But we'll see in the next video when we look at how the theory meets the reality. And I'm sorry that I didn't write a script and all that. I had a good video in my head. I just couldn't put it on paper, literally. So I hope this helped somebody, and if not, somebody will tear me apart in the comments and give you the right answers in case I just blatantly lied to you. So 7-3 for now. This is K5 UCO.